I am a big fan of core reinforced filaments, and this time I can test them across 4 different base materials. Welcome to my tech fun, to I think quite special filament testing video. I have here 4 spools from BIQU. These are CarbonCore25 filaments, 4 base materials, PLA, PETG, ABS and PA or nylon. And I bought these filaments myself, and 2 weeks later they contacted me if I want to test their new filaments. Well, I told them yes, but I already bought them, so they don't have to send it to me. So this is not a sponsored video of any kind by BIQU, but it is still a sponsored video. Actually, the whole channel is sponsored by Polymaker and by my Patreon supporters. And now let's talk about these filaments. According to the website, the concentration of the fibers is between 15 and 25%, and they are located in the center of the filament. This is the point of the core filaments. Outside we have some skin from the base material. These have its own advantages, but I will mention them later. Additional information from the website. The size of these shop fibers is between 0.3 and 0.5 millimeters. This is bigger than average, and with normal filaments I would worry about the clogging of the nozzle if I use 0.4 mm size. But this is core filament and these fibers should stay inside. The flow is laminar, and I even asked BIQU and they confirmed that we can use 0.4 mm nozzle. Of course, I would avoid definitely those CHT-like high flow nozzles because we have that island, and for this I don't recommend using the 0.4 mm nozzle with core filaments. The risk of the clog is a little bit higher. The whole testing I will do with 0.4 mm nozzle with all 4 filaments, and probably I will push at least 15 or 20 hours in it, and we will see if I will have a clog or printing will be fine. Now let's see the advantages of the core filaments. Non-abrasive surface because we have that base material outside, and they even claim that this is AMS compatible. Now with AMS compatibility we need 2 properties. One is less friction between the filament and Teflon and parts inside, and for this the core filaments are good because we have smoother surface outside. But the other thing is how brittle is the filament, and actually I will measure this because if it is too brittle then the risk of breaking inside the AMS is a little bit higher. And I will measure all 4 filaments with my tool, and I have now reference numbers too. Another advantage of the core filaments is better layer adhesion. And I actually tested this in a separate video when I printed these DIY core filaments, because outside we have the skin from the base material. Because carbon fibers will usually reduce this cross section and reduce the layer adhesion. But if only the base material we have the contact, and they will because the flow is laminar and we will have better strength along the z-axis. And let's don't forget the carbon fiber advantages versus non-fiber reinforced materials. Higher strength, the most typical is a resistance to the bending, less shrinking, this means easier printing, less warping, and better dimensional accuracy. But usually these carbon fibers will make the part more brittle, this means it resists less to the impacts. Additionally, I noticed that they are more sensitive to the moisture. Even PLA ABS is not so sensitive to moisture, but in the fiber reinforced version it is, especially with the core version. I'm not sure why, this is just my experience, but I notice every core filament, if I leave on open air 2 or 3 weeks, I have to dry before the printing, even if it is, glass fiber ABS. The reason may be that the moisture will go inside these channels between the fibers and the filament or something like that, but I always notice that I have that over extrusion, very ugly surface, because those micro water drops will boil inside the nozzle and push out more materials. So pay attention that all carbon fiber filaments you have to dry before the printing or store it on very dry place. For the moment I will show you the price because I think it is quite good, but of course you have to check it for your country. For PLA and PETG price is the same, ABS a little bit higher, and then PA or nylon again a little bit expensive. The information for each filament type is given on this very long web page, which is not too practical because we have to do a lot of scrolling to find the information we are looking for. For example, this is just for the PLA, and same scrolling I have to do for the PETG or ABS, so I collected them in one Excel table. In the first table you can see the recommended print settings, nozzle temperature, bed temperature and the flow rate. And I will always use the highest value for recommended range. This is for the print temperature and also for the flow. And in this table I collected the mechanical properties and I try to highlight important values. First we can see the density, and ABS is the lightest. Heat deflection temperature, huge difference of course between the PLA and the nylon. Now this is higher value compared to the average PLA, and this is my experience too, that the carbon fibers always increase a little bit this heat deflection temperature. Tensile strength. Now in this table the PLA is the weakest and the nylon is the strongest. My experience is different. PLA is actually quite strong material with a higher tensile strength. Maybe these core fibers will reduce it, I don't know, but it will be measured too. This is the breaking elongation rate, a very high value for the PA. This means it will prolong quite a lot before the break. And this is the bending strength, again the highest rate from the PA or nylon. This is PA12, I have that information, which is less sensitive to moisture compared to the PA6. But usually the PLA have quite big bending strength. This will be measured too. And these properties are just my comments. I know that PLA have the lowest temperature between these four base materials. PETG, it is more brittle and properly require drying. About the ABS, quite good material, but we have to see how much smell we have during the printing, and of course it is recommended to print it inside enclosure and ventilate the room after the printing. And about the nylon, usually experience more creeping with the nylon, and it is very moisture sensitive, especially in the core carbon fiber version. Let's start with unboxing PLA. Vacuum packaging, the bag is not resealable. Very smooth surface for the touch. Even the nylon is in this simpler packaging. For the touch, each filament is quite smooth, but the PETG and ABS are very shiny. The PLA is matte and the nylon is somewhere between. Now maybe you can see on the camera that we have less filament from the PETG compared to the ABS, because here the density is lower, and to have the same weight we have more filament from this material. Quick check how brittle is the filament. I'm starting with the PLA. Oh, not brittle. I don't even have to measure it. PETG. Also not brittle. ABS. Okay, not brittle. Yes, I can see some whitening on the surface. This is typical for the ABS materials. And nylon. Not brittle. I don't have to measure them, great. So no need for the measuring, they wouldn't even break in my tester. And I can confirm that basically each of these filaments can go into the AMS. And now I noticed some additional information about part cooling fan, which is 40% in each case, which is a little bit weird. I think I will use the generic profiles for these base materials. Only the print settings and the maximal flow will be according to these numbers. 3 filaments are loaded into the AMS, PLA, PETG and ABS. Only the polyamide or nylon will be dried before the printing. Print settings for the PLA: 60 on the bed, 230 on the nozzle, 15 the maximal flow and the maximal part cooling. And of course my typical test objects. Last few vertically printed test objects. And they look completely okay. The bed is still 45 degrees Celsius, but oh, it's completely removable now. And check this quality of the overhangs, real beauty. Starting from generic PETG profile, 70 on the bed, 250 on the nozzle, 12 will be the maximal flow, and the part cooling up to 40%. PETG printing is fine too, without any drying, but I will measure the dimensions later. I think we have a perfect example of the wet carbon fiber reinforced PETG, and I will reprint this after the drying, but I will take a closer look first. This is what I was talking about. The printing is finished, but look at this surface, so definitely even out of the box it is full of moisture and needs to be dried. I think some kind of aluminium packaging would be better instead of this plastic foil. And I will stop the printing now, and all 3 rest filaments will go into the dryer for at least 6 hours. I removed the PLA, and these are PETG, ABS and nylon, because they can be dried on a little bit higher temperature. Drying on PETG settings, 65 degrees Celsius, and rotating the spool, okay. I gave it additional 3 hours of drying, so the total drying time will be 9 hours. But if it is not dried properly, the polyamide will need more. Even if I know the result, I am always amazed with the quality improvement after the drying. I almost have to remind me that this is the same material. Side by side, this is the wet side and this is the dried side. Same material, and I would suggest to the BIQU to dry the filament before the packaging and use some aluminum based bags. Just to see the effect of the drying to mechanical properties, I will do a few tests with these wet filaments too. From each filament I will print this open-end wrench. They will be included in this comparison video. Star profile Bamlab ABS GF, 60 chamber temperature, 90 on the bed, 260 on the nozzle, 12 the maximal flow, and the part cooling maximal 30%. The start is great, absolutely no signs of the warping, and of course the actually heated chamber and carbon fibers will prevent this. Now minimally, but I can feel that smell of the ABS. Unfortunately I still didn't solve the ventilation problem with my H2 printers. Only my X1 carbon is connected to that ventilation hole. It's almost finished and this filament is dry too. It was finished a few seconds ago and I want to check the bed adhesion. By the way, even now the smell is not so strong when I open the doors and the bed adhesion is still great. I have to wait until it cools down. Partly I took it out, the cooling will be faster. Okay, perfectly removable. And now nylon, it was in a separate dryer because AMS cannot dry during the printing. Nylon, generic PACF is the salt profile, 60 chamber temperature, 90 on the bed, 12 the maximal flow, and the nozzle temperature reduced to 260 because this is the maximum recommended for this material, and the part cooling up to 30%. Very short layer printing time, maybe this will be a mistake. It started. The initial adhesion to the bed is good. It's always hard to wait. This will be weak. As predicted. No adhesion. Adding some glue and I will increase the bed temperature, and if that will not help then I'm moving to the engineering plate. And this time it will be finished correctly. At the end I will check the bed adhesion. But I think I don't like this surface, it needs a little bit more drying probably. Printing is finished a few seconds ago and probably the bed adhesion is good. Yes, but this surface quality not. Somehow I had this feeling when I saw the packaging, this surface quality is not acceptable, it needs much more drying. So I don't know what is the maximal drying temperature for the spool. Additionally, this kind of a spool will result in drying only of outer loops because it is too close. I hope 70 degrees Celsius for 12 hours will give us some better result. Probably outer loops are more dried, but it's time to test it again. Looks a little bit better, but far from perfect. I don't know how they stored this filament, but the improvement is hardly visible. This is the first version, and this is after additional drying on 70 degrees Celsius, almost 12 hours. I'm not really surprised. Depend on the start moisture, but drying on 70 degrees Celsius sometimes requires even 1 week. Tested in 2 videos. One last attempt, drying in Sanlu E2 filament dryer on a little bit more than 90 degrees Celsius. I hope spool will survive this temperature. It is still hot, I cannot touch it. I started with 96 degrees Celsius measured and I rotated the spool every 15 minutes and I noticed that it started to be damaged, so I reduced the temperature to approximately 87 degrees Celsius measured, and after 6 hours, if this not helps, then I don't know, nothing will. Soon it will be finished and I'm still not sure is it better or not. Now it starts to look like acceptable quality, but this is still far from perfect and this drying is not really enough. But I will stop with the drying here and I will print my test objects. I'm not sure how they store the filament after manufacturing, but this is not really acceptable. And I noticed some warping with one of test objects, very minimally, but definitely I need better bed adhesion, so I will use engineering plate with the glue on it. I know that the printing will be fine. Engineering plate works great, and don't forget it is available now for H2 printers too. Printing will be finished soon, and I'm not too happy with this surface quality. Probably I will measure some over-dimension because of that over-extrusion, because of the moisture. I don't really like that last object. Yes, layer printing time was too short. Bed adhesion check. Yes, it's good. I have to wait until it cools down. I forgot to record. Bed adhesion is fantastic. Engineering plate. It saved me so many times with some different filaments. This time the print quality is on edge of acceptable, but definitely I can see that it needs more drying. Well, except with this object here the surface quality is very bad, but not because of the moisture. Well, actually it is partly, but I should increase the layer printing time. But without further drying, I just don't want to invest more energy into this filament. One more thing I noticed during the video editing: pay attention how bottom looks better. Probably only outer loops of the filament got better drying. That's why with the nylon, drying during the printing would be important too. Actually, I have 3 filament dryers waiting for the review. They can reach the temperatures up to 85 degrees Celsius, and I will try to use one of them to dry exactly this filament, and I will even try to measure the moisture content. They are all labeled, and I will wait now 2 weeks before the testing, so they will absorb some moisture, especially in nylon, and they will become closer to that stable state. Tensile test with horizontal printed objects. On the left side you can see the compression numbers, and as you requested, no background music. Surprisingly low numbers for the PLA and the ABS. PETG very good, but look at this, drying helps. The difference is not big but noticeable, and similar value for the PA. Layer adhesion with vertically printed objects. Now wet. This is my rating for this size of the test object, and again a little bit lower numbers for the PLA and ABS, but these are still acceptable too. And look at this fantastic layer adhesion for the PETG, and for the layer adhesion it is very important to dry the filament. And the PA also fantastic layer adhesion. Shear test horizontal printed objects. Shear test, but with vertical printed test specimens. When printed in horizontal position, fibers always helps a lot here, and fantastic value from the PA or nylon. Now printed in vertical position, the layer adhesion is very important, and fantastic value from the PETG. Now PA, this could be even better probably, but remember that because of that minimal layer printing time, which was too short, I have very ugly last 2 vertical test objects, but without any further drying, I didn't want to invest more energy to this. Torsion test and frost with horizontally printed objects. Loads at 90-degree rotation. At the maximal loads in Newton meters. And now printed in vertical position. ABS 1.7, 1.6. Torsion test, printed in horizontal position, load at 90-degree rotation. These are good values except for the ABS. Now printed in vertical position, again very similar numbers like with this one printed in horizontal position, and even the ABS is, let's say, acceptable here, but I was expecting a little bit more from this material. 3-point bending test. Distance between supports is 50 mm, and I'm placing the loads and I'm measuring the deformation after 1, 30 and 60 seconds. Currently this is under 5 kilograms and the deformation under 10 kilograms. I really like this test because it tells me a lot about any material. For example, smallest deformation we can see on PLA and PETG. Even under 10 kilograms we can see very minimal additional deformation during that 1 minute. About ABS and nylon, we can see quite a lot of additional deformation during that 1 minute under 10 kilograms. But look at this, ABS under 5 kilograms, almost no additional deformation. This is almost horizontal, unlike with the nylon. This means this is not really the creeping of the ABS, but this 10 kilograms just became too big load for this material. Unlike with the nylon, which also likes to creep, which you will see soon. Creep as a deformation under constant load, PLA, PETG, ABS and nylon. (14.87), 15.02, 16.01, 18.14. This is day 5, very typical behavior from some materials like from this nylon, but let's measure them and then we will analyze the numbers. 16.36, 15.72, 17.44, 25.73. Removing the load. And their deformation after 5 minutes. On this graph we can see the distance between two reference surfaces, and of course biggest deformation is on the nylon, and the smaller, well, depends. Look at this initial deformation, smallest is on the PLA, but with the more creeping it has more deformation later. But actually the creeping we can follow on the second graph. Difference between 2 days is presented here, and of course we can see the biggest creeping on the nylon. This is what I was familiar. And here, let me change this a little bit and then we will see better what's happening here. And look at this, on day 5 the smallest deformation is from the ABS, and between these 3 biggest on the PLA. And on a little bit higher temperatures this PLA creeping would be even much bigger. Now the IZOD impact test, and I will show you just one break from each material, and then I will show you 4 pictures from the screen with 3 results. PLA, PETG, but for this test I have before and after drying. PETG wet, PETG dry, ABS, nylon. Wow, so weak that it's not even measurable. Nylon again. It is still so wet that it is over extruded and too big for this holder normally, and it's stuck inside. Okay. Not really measurable data, and the first one break even without number. PLA, PETG dry and wet, ABS and nylon. And now moving to the Charpy hammer. Charpy PLA, PETG, and here I have only the dry version, ABS, nylon, and in this holder I don't have a problem with the over extrusion, but still brittle. PLA, PETG, ABS and PA or nylon. In most cases very typical numbers. The toughest is the ABS and the most brittle PETG, but even here the drying helps a little bit. And as always the PLA is tougher material compared to the PETG. Only nylon was a little bit disappointing. I think this would be much higher if it would be completely dried, but for this it should arrive on much better spool. I mean, drying on 85 degrees Celsius is just not enough to dry it in some reasonable time. Temperature test in the oven, from left to right, PLA, PETG, ABS and nylon. And I want to record the temperature of the first noticeable deformation. And of course the first one was the PLA, shortly after that the PETG, and then the ABS. And I decided to take out these filaments because I'm expecting much higher deformation temperature of the nylon. Let's jump in the time. And a little bit above 200 degrees Celsius I noticed that it starts with deformation. And I stop to check how flexible it is. This is the most obvious difference between these 4 base materials. And thanks to the fibers, in every case the temperature is a little bit higher than with the average base material. Our results one more time: creep test, tensile and layer adhesion, shear test horizontal and vertical, bending test to deformation after 30 seconds, bending test deformation after 1, 30 and 60 seconds under these loads, torsion test horizontal vertical, temperature test, and the impact tests, IZOD and Charpy. Just very quick conclusions, because this video starts to be too long. This is scary property for many potential viewers, but this was huge work too. So about their PETG, I really like this material, but it is important to be dried. About this ABS, I don't really like this material. I was expecting a little bit more from this. About the PLA, I don't really see the purpose of adding these fibers to this PLA. Some properties are a little bit improved, but some are much weaker. For example, the tensile strength, which is, I think, important property. And about the nylon, well, this is very special material. I can see a lot of possibilities in this material, but as I mentioned, it must be properly dried. But even in this, let's say, half wet state, it has quite good mechanical properties and layer adhesion. But first step should be done by the BIQU. First of all, dry the filament before the packaging, and after this maybe they should use some better packaging, maybe some alu foil or something like that. And maybe they should use some better spools, maybe some cardboard spools which can be dried even on 120 degrees Celsius in the oven, because this closed plastic spool, which cannot survive even temperatures above 90 degrees Celsius, are just not good enough. I mean, drying on 85 degrees Celsius inside this closed spool, maybe it is possible, but let's say in 5 days or something like that. So I can see a lot of possibilities in this filament, but it must be properly dried. Actually, I have an inline dryer on the test. Maybe I'll try to use it with this filament. We will see, because it is independent from the spool. But more about that in some future video. So anyway, thanks to all my Patreon supporters, because thanks to their donations, I really don't mind doing this big work too. And to all the others, thank you for watching this video until the end, and I know, happy printing.